So now we can move on to our final important observable. This is the fact that the universe is homogeneous and isotropic. And again, you might be thinking, hang on, my lecturer has lost the plot again. This is a bit like the night sky is dark, because this, firstly, is a very obvious, simple statement to make, and secondly, it actually seems obviously wrong. Because let's just take into account what that actually means. So the fact that the universe is homogeneous means that there is no preferred location. So something that's homogeneous is basically the same everywhere. There is no preferred location in it. And the fact that the universe is isotropic means that there is no preferred direction. So for example, if I have a set of squares here, I have some lines like this. As long as I'm in this pattern here, and as long as I'm sampling a region that's much bigger than the lines, this is something which is homogeneous. It kind of looks the same everywhere, as long as I'm bigger than the lines. But on the other hand, it does have a preferred direction, because clearly the lines run in one direction. On the other hand, if what I have is a set of concentric circles, something like this, okay, they're not quite right, then this, from the middle, is isotropic, because it doesn't matter if I look this way, or this way, or this way, it's always the same. And, as I say, this doesn't appear to match the universe at all, because, on the Earth there are plenty of preferred directions, up and down, for example. There are plenty of preferred locations. Unfortunately, many of our currently preferred locations may not be available to us. And therefore, it doesn't look like it's true. So in the local universe, this just isn't true. Either in our day-to-day experience or even in the universe. And so it is clearly a simplifying assumption of cosmology, and it might be an assumption which is wrong. So, for example, you've got the sun, a preferred location in the solar system. You've got the galactic centre, for example. They do provide preferred locations and directions. And even on scales which are bigger than that, for example, this here is the local group. You probably can't see that very well. Let me see if I can make it a little bit bigger. It's the local group of galaxies. And if I just zoom in on that, you don't need to see it terribly well. But what you will notice in the local group of galaxies, for example, is you've got the Milky Way, which sits down here. This up here is Andromeda, also known as M31, and you have a load of other little galaxies that sit within it. There's the NGC 300, which sits over here. So these things sit over here. You could also imagine that you might draw an axis in here between the M31 and the Milky Way. They're the two biggest galaxies that are in there. And so when you look at the local group is neither homogeneous nor isotropic. But cosmology is not just about studying galaxies near us. I've already said it's not about studying any individual galaxy particularly. It's about studying the universe on large scales. And so it's a simplifying assumption which becomes better as you go further out. And so this diagram here, again, it's not the best diagram in terms of the high quality of it, but it's a figure from something called the 2-degree field redshift survey. And this is something on the Anglo-Australian telescope. It's a telescope in Australia which has lots and lots of spectrographs. Basically, you put a little bit of fibre optic cable on a galaxy and you take the spectrum of that galaxy. And so you measure the positions and the redshifts of a very large number of galaxies. And what you see here, there are some structures in here. So you see things called filaments and voids. So you see some sort of preferential structure, but not very much. So this is close to homogeneous and isotropic. It's not perfectly homogeneous and isotropic, but it is close to homogeneous and isotropic. And so it is a good approximation on sufficiently large scales. And so you can then ask, well, what about on even larger scales? And there is an even more extreme version which you can look at, and that is this. Some of you may have seen this figure before. It's a very famous figure. It's called the cosmic microwave background. Often just abbreviated CMB. It's a microwave signal. And that basically is a set of photons of very low energies which permeate throughout the universe. It was kind of discovered by accident. In fact, it was a background in a radio telescope that people couldn't get rid of. And in fact, people worried a lot about when they first found it that they couldn't get rid of this background, and they actually had to clean off the dish because they thought it was something they referred to as a mysterious white dielectric, by which they meant the pigeon poo sitting on their dish. They didn't get rid of it, so cleaning the dish didn't help. This was in fact a real astrophysical signal. And what it is it's a signal from the very early universe. It's actually a very useful signal, and again, it's a feature that we'll return to throughout the course. So I'm not going to try and tell you everything we need to know about the cosmic microwave background now, but it's very important for this idea that the universe is homogeneous and isotropic, because it gives you a picture of what the universe was like, perhaps only a few 100,000 years after the Big Bang. So in the early universe, well, everything that we see in the universe now was crammed down together, so it was hot. And that means that electrons and protons are separated. So you might have a globally neutral universe, but you have lots of free electrons and free protons which are charged. And when you have that, you have scattering. It's called Thomson scattering. And all that means is you have a photon plus an electron, and it scatters to give you another photon and another electron. So that looks the same. These are photons. But that scattering changes the energy of the photon, and it changes the energy of the electron. What it also means is that if I try and shine some light, for example, through my ionized medium, my medium of electrons and protons, I don't get very far before I scatter off an electron. So the universe is opaque to electromagnetic radiation. And so you have lots of photons scattering. And for reasons that we'll come back to later, you have about 10 to the 9 photons per proton, or baryon we'll call that. So there's lots and lots of photons and not very much matter. As the universe cools, you get to the point where you have this reaction, electron plus a proton, to give you hydrogen, i.e. an electron and a proton, plus another photon. And I'm going to stress something that's quite important here. These photons are not dominant in the CMB. So quite often, if you ask an exam question that says, explain the origin of the cosmic microwave background, I see people write this equation and then tell me that these photons here are the cosmic microwave background. But because there are 10 to the 9 photons per baryon, per proton, what actually happens is that the universe cools down. At this point it becomes neutral, and that means the universe becomes transparent. And then all these photons, all these billion photons per proton, can get out. They escape and they stream to us. And until the moment they escape, they've been entrained with all this matter. They've what we call thermalized. So they're telling us something about the conditions in the universe before this process called recombination happens. So this is called recombination. It's a terrible name because the universe has never been combined in the first place, but it's called recombination. After recombination, the universe is transparent, photons stream through us, and they tell us what the temperature of the universe was in a certain direction at a certain time. And that's very useful because we can then measure that temperature, and that's what's here in this diagram. The little bits that are red are hot, the little bits that are blue are cold. So it looks kind of homogeneous and isotropic, but you know, there's still some variation in there until I tell you that the contrast in that image has been turned up by a factor of 100,000 or something like that. And so what I'm actually looking at when I look at this is I am looking at tiny variations in the temperature. And they're about 1 part in 10 to the 5. 1 part in 100,000 hotter in the hot bits than it is in the cool bits. So the early universe was both homogeneous and isotropic. And we call that, it's got a name, the cosmological principle. And it's absolutely vital when it comes to writing down equations that govern the evolution of the universe, because assuming that it is isotropic and homogeneous means that we can write simple equations down to govern it. So a very quick summary of what we have learned in this lecture is that the universe is a finite age. It is expanding from a point of a Big Bang 14 billion years ago, and it is isotropic and homogeneous. And that's the starting point for the model of how the universe evolves that we'll get to in the next lecture.